Our planet is a fragile oasis adrift in a silent, black ocean. Yet the discoveries we are making beyond our atmosphere are not just rewriting astronomy textbooks. They are actively shaping the destiny of every person on Earth. This is a journey through 30 of the most profound space discoveries, from hidden oceans on distant moons to the echoes of the universe's birth. By the end, you will understand how these cosmic revelations hold the power to redefine our technology, our philosophy, and our very survival. We will visit a world with lakes of liquid methane and ask if a mysterious interstellar object was a natural rock or something else entirely. What does our future look like when it is written in the stars? Just 4.2 light-years away, a world exists that could mirror our own. This is Proxima Centauri b, an Earth-sized planet orbiting within the habitable zone of the star next door, Proxima Centauri. Its discovery was not just another entry in the growing catalogue of exoplanets. It was a profound shift in perspective. For the first time, we could point to a specific, relatively nearby point of light and say, there, right there, is a world where conditions might allow liquid water, and therefore life as we understand it, to exist. The implications are staggering. This isn't a hypothetical planet hundreds of light-years distant. It is practically in our cosmic backyard. That proximity changes everything. It transforms the question of life in the universe from a philosophical pondering into a tangible, addressable scientific target. We can study this world, analyze its atmosphere from afar with next-generation telescopes, and one day perhaps even send a probe to visit it. Initiatives like Breakthrough Starshot, which envisions tiny, laser-propelled spacecraft reaching the system within a human lifetime, are no longer pure science fiction. They are ambitious engineering challenges born directly from this discovery. Yet Proxima Centauri b is no paradise. It orbits a red dwarf star, a type known for its violent temper. Cataclysmic stellar flares, hundreds of times more powerful than anything our sun produces, routinely blast the planet with intense radiation. This harsh environment poses a critical question: could any atmosphere or any life survive such relentless bombardment? The answer might lie beneath an icy crust or within deep planetary oceans, places where life on Earth also thrives in extreme conditions. Finding out is now one of astronomy's greatest quests. The existence of Proxima Centauri b offers a powerful duality. It presents both a beacon of hope and a brutal reality check. It tells us that Earth-like worlds are probably common, but also that the gentle stability of our own solar system might be a rare cosmic gift. If we one day confirm signs of biology on this neighboring world, it would mean life is not a miraculous accident confined to our pale blue dot, but a natural, widespread phenomenon. Conversely, if we find it to be a barren, irradiated rock, it would underscore the incredible fragility and preciousness of our own planetary home. This single discovery, this nearby world, forces us to confront our place in the cosmos with a new and urgent clarity. But the search for life does not hinge on a single world. While Proxima Centauri b offers a tantalizing solo act, another discovery revealed an entire cosmic family portrait, a planetary system so packed with promise it redefined our expectations. 40 light-years away, a faint, cool star named TRAPPIST-1 hosts not one or two, but 7 rocky planets, each roughly the size of Earth. This compact system is a miniature solar system in its own right, with all 7 worlds orbiting closer to their star than Mercury does to our Sun. Yet because TRAPPIST-1 is so dim and cool, several of these planets orbit within its habitable zone, that Goldilocks region where liquid water could theoretically exist on the surface. Imagine stepping onto one of these worlds and looking into the sky. You would see the other 6 planets as clear, distinct orbs, some appearing larger than our moon. This density of Earth-sized worlds in one place is unprecedented. It transforms the TRAPPIST-1 system from a mere curiosity into the galaxy's most perfect natural laboratory for comparative planetology. We can study 7 sibling worlds, all born from the same stellar nursery under similar conditions, and observe how they each evolved differently. One might be a dry, Venus-like furnace, another a frozen wasteland, and another, just maybe, a temperate world with oceans and skies. By comparing their atmospheres side by side, scientists can begin to answer fundamental questions. What factors make a planet habitable? Is life a common outcome on suitable worlds, or does it require a bizarrely specific chain of events? Right now, the James Webb Space Telescope is turning its golden eye toward this system, not for a quick glance, but for a deep, atmospheric investigation. As these planets transit or pass in front of their stars, starlight filters through their atmospheres. Webb's exquisite instruments can dissect that light, searching for the chemical fingerprints of molecules like water vapor, carbon dioxide, methane, and oxygen. The detection of certain combinations, like oxygen and methane together, which normally destroy each other unless constantly replenished by life, would be a revolutionary hint of biology. The TRAPPIST-1 system represents a staggering statistical reality. If one quiet, common type of star can host 7 Earth-sized planets, several in the habitable zone, then the number of similar worlds across the Milky Way must be astronomical. It suggests that the ingredients for life are not rare treasures, but common construction materials scattered throughout the galaxy. The answers we find there, whether we see barren rocks or signs of a living world, will tell us if we are cosmically lonely or if the universe is quietly, abundantly teeming with possibilities. The search for life, however, begins right in our own celestial backyard with a discovery of astonishing practicality. While we scan distant stars for signs of habitable worlds, we have confirmed the existence of a vital resource much closer to home, hidden in the deepest, coldest shadows of our moon. For decades, the moon was considered a bone-dry desert, a place where astronauts left footprints in dust as fine as powder and as dry as ash. That perception has been utterly shattered. Orbiting spacecraft have detected definitive evidence of vast deposits of water ice, not just scattered molecules, but potentially millions of tons of it, locked away in the permanently shadowed craters at the lunar poles. These are places where the sun has not shone for billions of years, where temperatures hover near absolute zero, creating deep freeze traps that have captured and preserved this precious substance. This is not merely a scientific curiosity, it is a game changer for human destiny in space. Water is the currency of survival and exploration. With accessible ice on the moon, the entire economic model of spaceflight shifts. Instead of launching every single drop of water, every breath of air, and every kilogram of rocket fuel from Earth at astronomical cost, we can learn to live off the land. This lunar ice can be mined and processed. It can be purified into drinking water for astronauts. Through electrolysis, it can be split into oxygen for breathing and hydrogen for rocket fuel. Think of it as a cosmic gas station and life support depot, already built and waiting for us just 3 days away. This transforms the moon from a destination into a base of operations. Suddenly, the vision of a permanent lunar outpost, a gateway to the solar system, becomes not just feasible but logical. From this base, we could launch missions deeper into space with rockets refueled by lunar resources, making the journey to Mars far more efficient and sustainable. The race to access this ice is already heating up. Multiple international missions, from NASA's Artemis program to ventures by other space agencies and private companies, are now specifically targeting the lunar South Pole. Their goal is not just to map the ice with greater precision, but to develop the technologies to extract it, to literally turn moon dust and ice into a thriving human presence. The discovery of water ice on the moon reframes our relationship with the cosmos. It teaches us that the resources we need to become a spacefaring civilization are not always on our home planet. they are scattered throughout the solar system, waiting for us to learn how to use them. This isn't just about going back to the moon, it's about learning how to stay. Mars has never stopped whispering its secrets to those willing to listen. For decades, our robotic emissaries have scoured its rusty plains, and what they have found is rewriting the story of the red planet from a dead world to one that was once profoundly alive. The rover's curiosity and perseverance have made a discovery as fundamental as it is tantalizing. They have drilled into ancient Martian rocks and detected complex organic molecules. These are not fossils of life itself, but something almost as significant: the preserved building blocks of life. Think of them as the scattered Lego bricks left behind after a grand creation has been dismantled. They include carbon-rich compounds, the essential ingredients from which all known biology is constructed. Their presence in 3-billion-year-old lakebed mudstone tells a clear story that Mars once had the chemical potential, the raw materials for life to emerge. This transforms Mars from a simple geological curiosity into the scene of a cosmic mystery. If the ingredients were all there and liquid water flowed for perhaps 1 billion years, did the recipe ever get followed? The plot thickens with another, more volatile clue. Orbiting spacecraft and surface rovers have independently detected something baffling in the thin Martian air: methane. On Earth, the vast majority of methane in our atmosphere is produced by living organisms, from microbes to cows. But methane can also be made by geological processes like certain rock-water reactions. The Martian methane behaves mysteriously. It appears in localized puffs and shows seasonal spikes, waxing and waning with the Martian summer. This pattern is incredibly difficult to explain through geology alone, which tends to be steady and diffuse. A geological source would likely produce a constant, low-level background, not these sudden, seasonal plumes, so the detective story deepens. Is this methane the faint, lingering breath of subterranean Martian microbes, tiny organisms eking out an existence in briny aquifers deep below the frozen surface? Or is it merely the ghostly signature of ancient water still interacting with olivine-rich rocks? Each new data point is a piece of evidence. The Perseverance rover is now collecting pristine rock samples, sealing them in tubes for a future mission to bring back to Earth. In our most advanced laboratories, we will search those samples not just for more organic building blocks, but for potential biosignatures, patterns or structures that only life could create. The discovery of organics and the enigma of methane force a profound shift in perspective. We are no longer asking if Mars was ever habitable. The evidence now strongly says it was. We are now asking the much more thrilling question: did it ever become inhabited? And if life did spark there, only to be snuffed out by a dying planet, what does that say about the fragility of biological beginnings? Or, in the most electrifying possibility, does it still cling to existence in the dark, wet places beneath our feet? Mars is no longer a distant red dot. It is an active case file, and every new discovery brings us closer to answering one of humanity's oldest questions. While Mars holds the echoes of a potentially wet past, another world in our solar system possesses a present-day ocean of staggering scale. Hidden beneath a cracked and frozen shell, Jupiter's moon Europa conceals a secret that has captivated scientists for decades. Evidence from the Galileo spacecraft, which orbited Jupiter in the 1990s, painted a compelling picture. Europa's surface is a labyrinth of crisscrossing fractures and jumbled ice blocks, resembling a global-scale ice pack on a turbulent sea. More critically, Galileo's magnetometer detected a telltale wobble in Jupiter's powerful magnetic field as it interacted with Europa. This wobble could only be explained by a global, conductive layer beneath the ice, and the best candidate is a vast, salty ocean. This is not a small subsurface lake, but a body of water estimated to contain more than twice the volume of all Earth's oceans combined, all trapped beneath an ice crust perhaps 10 to 15 miles thick. The implications are profound. Here, in the cold outer solar system, far from the sun's warmth, exists a dark, aquatic abyss kept liquid not by solar heat, but by the relentless gravitational kneading from Jupiter. This tidal flexing generates immense internal heat, potentially creating hydrothermal vents on the ocean floor, scalding, mineral-rich geysers on the seabed. On Earth, such vents are teeming oases of life, entire ecosystems that thrive in complete darkness, powered not by sunlight but by chemistry. This raises an electrifying possibility. Could Europa's sunless sea host its own alien biology? The case grew even stronger with observations from the Hubble Space Telescope. On multiple occasions, Hubble has captured what appear to be giant plumes of water vapor erupting hundreds of miles into space from fractures in Europa's southern hemisphere. It is as if the Moon itself is offering us a sample of its hidden ocean, spraying its contents out into the void for us to analyze. This discovery transforms a distant speculation into a tangible opportunity. We no longer need to drill through miles of ice to taste Europa's ocean. We might simply need to fly through one of these plumes. This is the core mission of NASA's upcoming Europa Clipper spacecraft. Slated to launch in the next few years, Clipper will conduct dozens of close flybys of the icy Moon. Its sophisticated suite of instruments will map the ice shell in detail, measure the ocean's depth and salinity, and most importantly, it will have the chance to directly analyze the composition of those surface plumes. It will search for complex organic molecules, the chemical precursors to life, and assess the overall habitability of this alien sea. Europa forces us to expand our imagination of what a living world can be. A habitable environment no longer requires a sunlit surface, a temperate climate, or even a breathable atmosphere. It can exist in perpetual darkness under crushing pressure in a world where the very bedrock is ice. If we find even simple microbial life thriving in Europa's abyss, it would prove that the recipe for life is not a rare and delicate formula, but a robust and universal process that can ignite wherever there is liquid water, energy, and the right chemistry. The search for life is no longer confined to planets. It has plunged into the hidden oceans of icy moons. Europa's hidden ocean may hold the promise of life, but another icy moon has already sent its secrets screaming into space. Saturn's brilliant white moon Enceladus is a world of astonishing activity. The Cassini spacecraft did not just observe this moon from a distance, it performed a breathtaking maneuver, diving directly through immense plumes of water vapor and ice crystals erupting from its south pole. This was no passive observation, it was a taste test of a distant ocean. Cassini's instruments analyzed that spray, and what they found sent shockwaves through the scientific community. The plumes were not just water, they contained tiny particles of silica known as nanograins and a significant amount of molecular hydrogen. On Earth, silica nanograins of that specific size are only known to form in one very particular environment, in the superheated water swirling around hydrothermal vents on the deep ocean floor. The molecular hydrogen is the clincher. It is the chemical food source, the energy currency, for microbes that thrive in those exact same dark, hot, mineral-rich environments. This is not a hint or a suggestion, it is a virtual announcement. Enceladus has active hydrothermal vents on the floor of its global subsurface ocean right now, today. This transforms a small, icy moon into arguably the most compelling target in our entire solar system in the search for life beyond Earth. Why? Because accessibility. On Europa, we hope to one day sample its ocean, perhaps by landing and drilling or catching a plume. Enceladus has already done the work for us. It is constantly and generously ejecting its ocean contents into space, where a spacecraft can simply fly through and collect them. The environment around these alien vents is almost a perfect parallel to the conditions where many scientists believe life on Earth began. If the recipe for life is as simple as liquid water, a rocky seabed, hydrothermal energy, and the right chemistry, then Enceladus has the kitchen fully stocked and the stove turned on. The question is no longer if the moon is habitable. The evidence screams that it is. The urgent, breathtaking question is it inhabited? Did life ignite in that dark, warm sea? A future mission could return to Enceladus, fly through its plumes with even more sensitive instruments, and search for the complex organic molecules or even potential cellular structures that would signal not just a suitable environment but its actual use. Finding life there, in a small moon orbiting a gas giant, would tell us that life is not a planetary phenomenon but an oceanic one. It could be as common as warm water meeting rock anywhere in the cosmos. While Enceladus offers a window into a warm, watery ocean, Saturn's largest moon presents a landscape of chilling and profound familiarity. Titan is a world shrouded in a thick, hazy orange atmosphere, so dense it hides its surface from prying eyes. But when the Cassini spacecraft pierced that haze with its radar, it revealed a scene both alien and eerily reminiscent of home. Titan has rivers, lakes, and seas, but they are not filled with water. In the deep freeze of -290°F, methane and ethane take on the roles we know so well, falling as rain, carving valleys, and pooling into vast, dark lakes. This is a complete, active hydrological cycle, just like Earth's, but built from an entirely different chemistry. It is a world where the very definition of a solvent, the liquid that dissolves and transports chemicals, is not water but liquid hydrocarbons. This makes Titan a frozen time capsule, a bizarrely preserved analog of a very early Earth before life rewrote the rules. Our planet likely had a thick, methane-rich atmosphere in its youth, and the complex organic chemistry now playing out on Titan's surface and in its atmosphere could mirror the chemical steps that led to the first building blocks of life here. To explore this primordial laboratory, NASA is preparing a mission unlike any other. Dragonfly is a nuclear-powered rotorcraft, essentially a large drone, designed to land on Titan's dunes and then take flight. The moon's thick atmosphere and low gravity make it an ideal world for flight, allowing Dragonfly to hop from one site of interest to another, covering tens of miles over its mission. It will land near Titan's equator among expansive dunes of organic sand, then fly to the edge of a deep impact crater where liquid water may have once mixed with surface organics in a warm, wet moment long ago. Dragonfly's instruments will not search for life itself, but for something just as revolutionary, the chemistry that precedes life. It will sniff the atmosphere, taste the surface material, and listen for subsurface quakes, piecing together the complex chain of reactions that create molecules like amino acids and nucleotides, the very Lego bricks of biology. This mission probes a fundamental question: can the pathway to life begin with a recipe that does not use water as its primary ingredient? Titan's existence expands the canvas of possibility for life in the universe. We have always been water-based thinkers, searching for liquid water as the sole indicator of habitability. Titan challenges that assumption head-on. If we find that its methane-based chemistry is actively creating complex probiotic molecules, it suggests that the universe might be capable of cooking up the ingredients for life in many different kitchens with many different solvents. Could there be forms of life on Titan, not in its frigid lakes, but perhaps in subsurface reservoirs of warmer water that use entirely different biochemical rules? Or does Titan show us the early, sterile steps of a process that, given enough time and a different climate, could lead to a truly alien biology? Dragonfly's journey to this hazy, hydrocarbon world is a journey into our own deep past and a test of life's cosmic potential. It asks us to consider that biology might not be a single, narrow road, but a vast network of possible pathways, some of which we are only beginning to imagine. The solar system's familiar dance of planets and comets was abruptly interrupted in 2017. A telescope in Hawaii spotted a faint dot of light moving at impossible speed on a trajectory that could only mean one thing. This object, named Oumuamua, was not from here. It was our first confirmed interstellar visitor, a cosmic wanderer that had journeyed for millions, perhaps billions, of years through the void between stars before slicing through our neighborhood. Its very existence was a profound revelation, proving that material from other star systems routinely passes through our own, but Oumuamua was strange. As astronomers scrambled to observe it during its brief flyby, the data painted a puzzling portrait. It appeared highly elongated, perhaps 10 times longer than it was wide, tumbling chaotically through space like a cosmic cigar. It showed no visible coma or tail, the classic features of a comet spewing gas and dust. Yet, as it departed, it exhibited a tiny but undeniable acceleration, a nudge that could not be explained by gravity alone. This is where the mystery truly ignited. For a comet, such acceleration is common, caused by outgassing, as sunlight vaporizes ice and the jetting material acts like a gentle rocket engine. But Oumuamua showed no signs of this outgassing, no detectable dust or gas cloud around it. So what was pushing it? The scientific debate exploded with possibilities. Some proposed it was a peculiar, dusty comet after all, with unusual composition. Others suggested it could be a shard of a Pluto-like world, a fragment of nitrogen ice ripped from a distant dwarf planet and sculpted by eons of cosmic erosion into its strange shape. Then came a more speculative, yet scientifically considered idea. Could the acceleration be explained by radiation pressure from the sun? For a naturally occurring object, this force is negligible. But for something extremely thin and lightweight, like a solar sail, it could be significant. This led a few scientists to cautiously raise the possibility, however slim, that Oumuamua could be artificial in origin, a discarded piece of advanced technology or a defunct light sail from another civilization. This was not a claim of discovery, but a call to consider all plausible hypotheses. The mainstream scientific consensus leans strongly toward a natural origin, likely a very unusual type of comet or asteroid from a system utterly unlike our own. But the key lesson of Oumuamua is not about settling a single mystery. It is a stark wake-up call. We have built a cosmic fence around our solar system and assumed we knew all the objects inside it. Oumuamua tore that fence down. It proved that interstellar traffic is real and we have been blind to it. In response, new projects are coming online like the Vera C. Rubin Observatory, designed to scan the entire sky with unprecedented depth and frequency. Its mission is to find more of these visitors, to catch them earlier and to study them in detail. Each one is a pristine sample from a star system we will never visit, carrying the chemical and physical history of its birth far away. Oumuamua was our first glimpse of the galaxy's grand exchange program, a silent messenger that passed through our backyard and left us with a single, humbling realization. We are only just beginning to see what is out there. Oumuamua's silent passage was a physical messenger from the stars, but decades earlier, a different kind of signal had briefly screamed into the void. In the summer of 1977, a radio telescope at Ohio State University, known as the Big Ear, was engaged in a quiet, systematic scan of the cosmos. Its job was to listen, not for the natural crackle of stars or galaxies, but for the artificial, narrow-band radio frequencies that might be the calling card of a distant civilization. On August 15th, the telescope's computer printed out a sequence of letters and numbers on a long sheet of paper. The data showed a signal so powerful and so perfectly tuned that a volunteer astronomer, Jerry Amon, famously circled the sequence and wrote one word in the margin: "Wow." For 72 glorious seconds, this intense, focused burst of radio energy, emanating from the direction of the constellation Sagittarius, saturated the receiver. It matched precisely what scientists had predicted an interstellar beacon would look like, a signal confined to a single, quiet channel of the radio spectrum, a feat nature almost never accomplishes. Then, as suddenly as it appeared, it vanished. Follow-up observations weeks and years later heard nothing but silence from that patch of sky. The wow signal became a ghost, a single, perfect note in an otherwise empty symphony hall. In the decades since, astronomers have chased countless natural explanations. Could it have been a reflection of a human satellite off a piece of space debris? The frequency used was protected, reserved for deep space science, making terrestrial interference unlikely. Perhaps it was a comet. Some suggested that hydrogen clouds around comets could emit a similar frequency, but detailed checks revealed no known comets were in that exact region of sky at that exact time. Other ideas pointed to a stellar flare or a microlensing event where a passing object focuses and amplifies a distant star's radio waves, but these phenomena are typically brief and broad, not a sustained, narrow-band signal. Each natural hypothesis has struggled to explain the signal's unique combination of intensity, frequency, and one-time occurrence. Its very perfection is what makes it so haunting. The WOW signal's true legacy is not as proof of contact but as a catalyst. It demonstrated that our instruments were sensitive enough to potentially hear such a call, and it underscored the profound challenge of the search. The universe is vast, and signals might be fleeting or deliberately brief. This single event helped galvanize the modern search for extraterrestrial intelligence, or SETI, shifting it from a fringe pursuit to a serious data-driven endeavor. Today, the search has evolved far beyond a single telescope listening to one frequency. Projects like the Breakthrough Listen initiative use the world's most powerful radio telescopes, from Green Bank to Parkes, to scan millions of stars across billions of radio channels simultaneously. They employ sophisticated algorithms that can sift through petabytes of data in real time, filtering out the constant radio chatter of Earth and identifying the kind of anomalous, narrow-band signals that the Big Ear detected that night. The goal is no longer to wait for another wow moment, but to systematically survey the cosmic haystack, looking for a needle that might be repeating, or one that was simply missed because we were not listening in the right place at the right time. The signal's enduring mystery serves as a powerful reminder. If a civilization did decide to send a brief, targeted beacon across the galaxy, it might look exactly like that one perfect, unrepeated burst. It fuels the quiet hope that somewhere in the mountains of data now being collected, an algorithm might one day find not a question mark but a pattern, a signal that returns, a hello that is waiting for a reply. While we listen for deliberate signals, the cosmos broadcasts its own explosive and enigmatic messages. From the deep reaches of space, far beyond our own galaxy, come fleeting blasts of raw energy so powerful they outshine entire stars. These are fast radio bursts, or FRB, and they represent one of the most puzzling discoveries in modern astronomy. Each burst is astonishingly brief, a cosmic flashbulb that lasts just a few thousandths of a second. Yet in that instant, it releases as much energy as our sun puts out over 80 years. For a long time, these events seemed completely random and one-time, like a single, deafening firecracker popping in the dark. Astronomers theorized they must be the final death cries of catastrophic events, perhaps a neutron star collapsing into a black hole or two incredibly dense objects merging in a violent collision. A single, universe-shattering boom, and then silence forever. That assumption was shattered with a single observation. In 2016, astronomers pinpointed a source that did the unthinkable. It burst again. And then again. This was a repeating fast radio burst, a discovery that overturned the cataclysmic model entirely. Whatever is creating these immense flashes of radio waves is not destroying itself. It is surviving the event and doing it over and over. This changed the entire investigation. Suddenly, scientists had a target they could monitor, a cosmic lighthouse that would unpredictably but reliably flash, allowing them to train the world's most powerful telescopes on its location. The leading suspect for these repeating bursts is a type of stellar corpse called a magnetar. Imagine a neutron star, the incredibly dense core of a dead star, but with a magnetic field so powerful it is a quadrillion times stronger than Earth. It is the most intense magnetic environment in the universe. Theorists suggest that starquakes on the surface of a magnetar, or sudden reconfigurations of its unimaginable magnetic field, could snap like a cosmic rubber band, releasing these tremendous bursts of radio energy. Some repeating FRBs fit this model beautifully, yet the mystery deepens because not all bursts are the same. Some come from seemingly calm regions of space with no obvious cataclysmic objects nearby, and their patterns of repetition are wildly irregular. This has opened the door to more speculative but fascinating ideas. Could some FRBs be produced by advanced technology? The concept is not that they are messages, but perhaps signatures of immense engineering, like power beams for propelling light sails on interstellar spacecraft, a technology we ourselves are beginning to experiment with. While that remains a remote possibility, the true scientific value of FRBs is already proven and profound. As these bursts race across billions of light years to reach us, they pass through the diffuse gas and invisible dark matter that floats between galaxies. This material leaves a subtle fingerprint on the burst, a dispersion that slows different radio frequencies by different amounts. By analyzing this effect, astronomers can use FRBs as cosmic probes to weigh the unseen material in the vast, empty spaces between galaxies, mapping the universe's hidden skeleton. Furthermore, the extreme conditions at the source of an FRB, where gravity and magnetism reach their theoretical limits, offer a natural laboratory to test the laws of physics in ways we could never replicate on Earth. Each millisecond flash is a coded telegram from the most violent neighborhoods in the cosmos, carrying secrets about matter, energy, and the fabric of space itself. Einstein's vision of the universe was one of dynamic geometry, a cosmic fabric of spacetime that could stretch, warp, and ripple. For a century, this final, unproven prediction of his general theory of relativity remained just that, a brilliant idea waiting for a whisper of confirmation. That whisper finally arrived in September 2015, a faint chirp lasting less than half a second. It was the sound of two black holes, each about 30 times the mass of our Sun, spiraling together and merging in a cataclysmic collision over 1 billion light-years away. The Laser Interferometer Gravitational Wave Observatory, or LIGO, had just made the first direct detection of gravitational waves. Think of spacetime as the still surface of a vast, dark pond. The presence of a massive object, like a star, creates a deep dimple like a heavy ball resting on a rubber sheet. But when truly massive objects accelerate violently, like two black holes whirling around each other at nearly the speed of light, they do not just create dimples, they send actual ripples racing outward through the fabric of the pond itself. These ripples are gravitational waves traveling at the speed of light, stretching and squeezing everything in their path by an almost unimaginably tiny amount. LIGO detected a distortion thousands of times smaller than the width of a single proton. This detection did more than confirm Einstein. It gave humanity an entirely new sense with which to perceive the cosmos. For all of history, astronomy has been the science of light. We have watched the universe through lenses and mirrors, collecting photons across the electromagnetic spectrum, from radio waves to gamma rays. But light can be blocked, absorbed, or scattered by dust and gas. Gravitational waves are different. They pass through everything almost completely unimpeded. They are a direct messenger from the most violent, dark events in the universe, places where light itself can be trapped forever. With this new sense, we began to hear the previously silent symphony of the dark universe. Most of the signals LIGO and its European counterpart, Virgo, have heard are the final, frantic orbits and mergers of black holes, events that emit no light at all. We would be utterly blind to them without gravitational waves, but then, in August 2017, the new era truly blossomed. the detectors picked up the distinctive chirp of a different kind of cosmic collision. Two neutron stars, the ultra-dense, city-sized cores of dead stars smashing together. Crucially, this event lasted much longer in the gravitational wave spectrum, giving observatories around the world and in space precious time to point their telescopes at the region of sky it came from. And there, for the first time, they saw it, a brilliant flash of light across multiple wavelengths, a kilonova. This was the birth of multi-messenger astronomy, observing the same cosmic event through both gravitational waves and light. The combined data told a complete, spectacular story. The collision forged and blasted out a cloud of material containing newly created heavy elements. Spectroscopic analysis confirmed the presence of strontium and other rare earth metals. The calculations were staggering. This single event likely produced an amount of gold and platinum equivalent to several times the mass of our entire planet. It was a definitive answer to a long-standing cosmic mystery. We now know that the gold in your jewelry, the platinum in a catalytic converter, and many of the heaviest elements in our world were not forged in the slow heart of a dying star, but in the violent, millisecond-long fireball of colliding neutron stars. Gravitational wave astronomy has pulled back a curtain we never knew was there. We are no longer just watching the universe, we are listening to its deepest vibrations, feeling the tremors from events hidden behind veils of dust and darkness. Each new chirp is a chapter in a previously forbidden book, telling us tales of how black holes are born, how the heaviest matter is created, and how the very fabric of reality behaves under the most extreme strains imaginable. The gravitational waves we now hear reveal a universe in motion, but they also depend on a fundamental cosmic speedometer, the rate at which space itself is stretching. This number, known as the Hubble constant, is the bedrock of modern cosmology, the key to calculating the age of the universe and predicting its ultimate fate. For decades, astronomers have worked to pin down this single, critical value with ever greater precision. Yet a profound and growing problem has emerged. The universe appears to be giving us two different answers. The first method looks back to the dawn of time, to the afterglow of the Big Bang itself, the cosmic microwave background. By mapping the subtle temperature fluctuations in this ancient light with exquisite detail, satellites like Planck can calculate what the expansion rate should be based on our best models of the early universe. That number is incredibly precise. The second method measures the modern, local universe. Astronomers use pulsating stars called Cepheids and cataclysmic supernova as standard candles, objects with known intrinsic brightness. By observing how much dimmer they appear at various distances, we can directly measure how fast space is stretching around us right now. Both methods are sophisticated, both are backed by mountains of data, and both should agree. They do not. The universe today is expanding measurably faster than our models of the infant universe predict it should be. This discrepancy is not a small glitch. It is a persistent gap that has survived years of rechecking and improved measurements. It has grown into a full-blown crisis dubbed the Hubble tension. Imagine two of the world's most accurate clocks, one built from the blueprint of the universe's birth, the other tuned by observing stars in our galactic neighborhood. They are both impeccably crafted, yet they tick at undeniably different rates. This is not just a problem with the clocks, it suggests a flaw in our understanding of time itself, or in this case, the fabric of the cosmos. The implications are staggering. This tension could be the first observable crack in our otherwise successful model of cosmology, a hint that something fundamental is missing from our equations. Perhaps dark energy, the mysterious force accelerating the expansion, is not constant as we assumed, but has evolved over time, growing stronger or changing its properties. Maybe there is an entirely new type of particle or field that we have not yet accounted for, something that subtly influenced the early universe and left its imprint on the expansion rate. Or, in the most radical possibility, it could mean our theory of gravity, Einstein's general relativity, while spectacularly successful, needs modification on the vastest scales. Any of these conclusions would force a rewrite of the cosmic rulebook. Solving the Hubble tension is now one of the highest priorities in astronomy. New telescopes, like the James Webb Space Telescope, are turning their gaze to those crucial standard candles, measuring them with unprecedented clarity to eliminate any potential error in the local measurement. Other projects are seeking independent ways to gauge the expansion, using gravitational waves from merging neutron stars as new standard sirens, or studying the large-scale clustering of galaxies. Each new data point tightens the knot or potentially begins to unravel it. This is not an abstract academic debate, it is a direct confrontation with the unknown. The discrepancy in this one number is a beacon pointing toward physics beyond our current understanding. It tells us that our map of cosmic history, from the first flash of the Big Bang to the present day, may have a missing chapter, a hidden ingredient that has been subtly steering the evolution of everything we see. The Hubble tension is the universe presenting us with a paradox, a quiet but insistent signal that the deepest truths about reality are still waiting to be discovered. Gravitational waves let us hear the universe's violent collisions, but to see its true hidden architecture we must look at the way it bends light itself. The cosmos is filled with an invisible skeleton, a vast network of dark matter that holds galaxies together and dictates their motion. We cannot see it, touch it, or detect it with any telescope because it does not emit, absorb, or reflect light. Yet we know it is there everywhere because of its overwhelming gravitational pull. Imagine watching leaves swirling in a river's current. You cannot see the water directly, but its movement reveals the powerful, invisible force guiding every leaf. That is how we map dark matter, by watching how its immense gravity distorts the very fabric of light from distant galaxies. This phenomenon is called gravitational lensing. When light from a faraway galaxy travels toward us, it passes through the gravitational field of a massive cluster of dark matter and regular matter. This field acts like a giant, lumpy lens in space, bending the light's path. The result is that images of background galaxies are stretched, magnified, and often warped into faint, smeared arcs and multiple copies around the foreground cluster. By meticulously measuring these distortions across thousands of galaxies, astronomers can reconstruct a detailed map of the invisible mass causing them. Projects like the Dark Energy Survey have used this technique to create stunning visualizations, showing the cosmic web of dark matter as a delicate, blue-gray filamentary structure spanning billions of light years, with galaxies clinging to its densest knots like dewdrops on a spider's web. Another line of evidence comes from the motion of stars within galaxies. The outer stars in spiral galaxies orbit their centers far too quickly to be held by the gravity of the visible stars and gas alone. There must be a vast, unseen halo of matter, a gravitational glue, preventing these stars from flying off into intergalactic space. This is the dark matter halo, an immense, diffuse sphere that envelopes every galaxy. So what do we actually know about this mysterious substance? We know it has mass and interacts through gravity. We know it is cold, meaning its particles move slowly compared to the speed of light, allowing it to clump and form the large-scale structures we see. And we know it is not made of the ordinary protons, neutrons, and electrons that constitute everything we see around us. It is something entirely new. And that is where our knowledge hits a wall. We do not know what fundamental particle it is. Is it a hypothetical weakly interacting massive particle, a WIMP that barely interacts with normal matter except through gravity? Or could it be an ultralight particle called an action, predicted by other theories of physics? Or is it something even more exotic, like primordial black holes formed in the universe's first second? Countless experiments deep underground and in space are hunting for a direct signal, hoping to catch the rare bump or flash of a dark matter particle interacting with a detector. Solving this puzzle is not just about cataloging an invisible component of the universe. It is a direct portal to new physics. Dark matter makes up about 85% of all the matter in the cosmos. That means everything we see, every star, every planet, every living thing, is just the visible frosting on a vast, dark cake. Unlocking its nature would not only tell us what most of the universe is made of, it could reveal forces and particles that operate on scales we have never before imagined, fundamentally rewriting our understanding of reality from the ground up. The invisible scaffold of dark matter defines where galaxies can form. But to understand if any of those distant suns host living worlds, we must learn to read their light in an entirely new way. For centuries, planets beyond our solar system were nothing but theoretical specks. Even after their discovery, they remained little more than mathematical ghosts, inferred from the wobble or dimming of their parent stars. The James Webb Space Telescope has changed that forever. It has given us the ability to transform those distant dots into worlds with weather, chemistry, and potential. Webb does not see these exoplanets directly as pinpricks of light. Instead, it uses a technique called transit spectroscopy. When a planet passes in front of its star from our perspective, a tiny fraction of the starlight filters through the planet's atmosphere. Different molecules in that alien air absorb specific colors or wavelengths of that light. Webb's immense mirror and exquisitely sensitive infrared instruments catch that filtered starlight and spread it out into a spectrum, a chemical barcode unique to that world's atmospheric composition. It is like standing outside a concert hall with the doors closed. You cannot see the orchestra, but by listening to how the music is muffled and changed as it passes through the walls, you can learn astonishing details about the hall's size, shape, and even the materials inside. One of Webb's earliest and most stunning triumphs was the analysis of WASP-39b, a hot, puffy gas giant orbiting close to its star. In the planet's spectrum, Webb detected the unambiguous fingerprint of carbon dioxide. This was a monumental first, not just for the detection itself, but for what it represents. Carbon dioxide is a key ingredient in planetary atmospheres, a regulator of climate, and on a rocky world in the right zone, a potential signpost of geological and even biological activity. Finding it so clearly and confidently proved that Webb could deliver on its promise to decode alien skies, but the telescope has done far more. It has spotted the hazy signatures of silicate clouds, like grains of sand vaporized into high-altitude mist on other blistering worlds. It has found hints of water vapor and methane in atmospheres where theorists predicted they could not exist, challenging our models of planetary chemistry. Most importantly, Webb is now turning its gaze toward smaller, rocky planets in the habitable zones of their stars, like those in the TRAPPIST-1 system. The goal is to search for what scientists call biosignatures, chemical imbalances that could be the waste products of life. On Earth, our atmosphere is wildly out of chemical equilibrium. It contains large amounts of oxygen, a highly reactive gas that should quickly vanish by bonding with rocks and other elements, and methane, which oxygen should destroy. The only reason both coexist is that life, through photosynthesis and other processes, constantly pumps them into the air. Finding a similar paradoxical combination on a distant rocky world would be the most compelling hint of biology we could hope for at such distances. This is not about finding a single molecule, it is about reading the complex story written in the ratios and combinations of many. A thick carbon dioxide atmosphere with traces of water might indicate a runaway greenhouse effect, a Venus-like hellscape. A thinner atmosphere rich in nitrogen with oxygen, methane, and water vapor would set every alarm bell ringing. With each new spectrum, Webb is teaching us that planetary diversity exceeds our wildest imaginations. We are learning that atmospheres can be stripped away by stellar radiation, replenished by volcanic outgassing, or transformed by the faint chemistry of a hidden biosphere. We are no longer just counting planets, we are beginning to understand their life stories, written in the delicate colors of their filtered starlight. Far beyond the orbit of Neptune, the solar system does not simply end. It fades into a vast twilight realm of frozen relics, a deep freeze archive holding clues to our very beginnings. This is the Kuiper Belt, a donut-shaped swarm of icy bodies where Pluto reigns as the largest known member. For decades, it was considered a quiet, distant frontier. Then, in 2015, the New Horizons spacecraft gave us our first close-up look at a Kuiper Belt object, a small world named Arrokoth. What it revealed was not a battered, cratered fragment, but a pristine, bilobed shape resembling a cosmic snowman. Its smooth surface and undisturbed form showed it was a gentle merger of two smaller bodies, a fossil from the solar system's earliest days when planets were just beginning to coalesce from the primordial cloud. Arrokoth is a time capsule telling us that the outer solar system has been cold and quiet for 4.5 billion years, preserving the building blocks of planets in their original state. But the serene story of this frozen belt holds a tantalizing disturbance. Astronomers tracking the orbits of the most distant Kuiper Belt objects, those that swing far beyond Pluto, have noticed something strange. A handful of these extreme objects share a peculiar orbital alignment. Their elongated paths are clustered together, as if something massive, something far out in the dark, is shepherding them, gravitationally herding them into a similar orientation. The math is compelling. The odds of this clustering happening by random chance are astronomically low. This has led to a bold and captivating hypothesis. The gravitational hand guiding them could belong to an unseen world, a so-called Planet 9. This would be no small discovery. Planet 9, if it exists, is theorized to be a super-Earth, a world with a mass up to 10 times that of our own, orbiting the Sun on a wildly elongated path hundreds of times farther out than Earth. Its presence would solve the orbital mystery, but it would also force a dramatic rewrite of our solar system's history. How did such a large planet end up so far away? One leading theory suggests it formed much closer to the Sun, alongside the giant planets, before a gravitational tug of war with Jupiter or Saturn catapulted it into the distant darkness, where it now follows a lonely, millennia-long orbit. The search for this phantom planet is a monumental challenge. At such distances, it would reflect only the faintest whisper of sunlight, making it incredibly dim. Its motion across the sky would be agonizingly slow. Astronomers are using the world's most powerful telescopes, like Subaru in Hawaii, to conduct painstaking surveys, comparing images of the same patch of sky taken months or years apart, looking for one tiny dot that has moved against the backdrop of fixed stars. Finding Planet 9 would be more than just adding a new member to our planetary family. It would be a profound lesson in humility. It would prove that even in our own cosmic backyard, major discoveries are still waiting in the shadows, that our map of the solar system is still incomplete. This hypothetical world is a ghost in the gravitational machine, a silent architect whose influence we can feel, but whose face we have yet to see. The frozen archives of the Kuiper Belt hold our past, but a different population of ancient rocks could unlock our future. Drifting through the inner solar system are thousands of near-Earth asteroids, and many are not just barren stones, they are floating mountains of raw material. Scientific surveys have revealed that certain asteroids are incredibly rich in platinum, iron, nickel, and cobalt, metals that are both valuable and essential for advanced technology. More critically, a class of asteroids known as carbonaceous chondrites are veritable water worlds, containing up to 20% of their mass as water ice and hydrated minerals. This discovery transforms a potential threat into a profound opportunity. The promise of asteroid mining is no longer science fiction. It is a logical next step in our expansion into space, and missions are already proving the technology. NASA OSIRIS-REx spacecraft successfully rendezvoused with the asteroid Bennu, mapped its surface in stunning detail and collected a sample of its primordial material, demonstrating that we can precisely approach, study, and extract resources from these small worlds. The upcoming Psyche mission will visit an asteroid of the same name, which is not a rocky body but believed to be the exposed metallic core of a failed planet, a literal mountain of iron and nickel orbiting the Sun. These are not merely scientific endeavors, they are pathfinder missions for a new economic paradigm. The practical implications are staggering. Accessing the water from a single, modest-sized asteroid could provide more liquid hydrogen and oxygen rocket propellant than all the fuel ever launched from Earth. This would enable the creation of orbital fuel depots, turning the space around our planet into a highway rest stop, drastically reducing the cost and increasing the range of all future missions. The precious metals mined from another asteroid could be used for in-space manufacturing, building satellites, space stations, and spacecraft without ever having to lift those heavy materials out of Earth's deep gravity well. The economic potential is measured in trillions of dollars, but the environmental argument is perhaps more compelling. Terrestrial mining for these same rare metals is one of the most destructive industrial processes on our planet, scarring landscapes, polluting watersheds, and consuming vast amounts of energy. By moving the heavy industry of material extraction off-world, we could preserve Earth's fragile ecosystems while still obtaining the resources needed to advance our civilization. This is not about abandoning our planet, but about protecting it by using the boundless resources of our solar system. The asteroids are not just rocks, they are the stepping stones, the raw lumber and brick for building a sustainable, spacefaring future for humanity. The silent sun is not a placid neighbor. Our star is a dynamic, churning sphere of plasma, and its temper tantrums can reach across 93 million miles to shake the very foundations of our modern world. This is the discovery of solar weather, a field of study that reveals our profound technological vulnerability to the whims of our own star. The most violent solar events are solar flares and coronal mass ejections. A solar flare is a sudden, intense flash of radiation, a burst of X-rays and extreme ultraviolet light that reaches Earth in just over 8 minutes. It can overwhelm the upper atmosphere, causing radio blackouts and disrupting navigation signals. But the real danger comes from its more massive cousin, the coronal mass ejection. A CME is a billion-ton cloud of magnetized plasma, a solar hurricane launched from the Sun's corona at millions of miles per hour. When this cloud is aimed at Earth, it can trigger a global geomagnetic storm, a tempest in our planet's magnetic field. We have seen its power before. In September 1859, a historic solar superstorm, now known as the Carrington Event, struck Earth. Telegraph systems, the high-tech communication network of the era, went haywire worldwide. Operators received shocks from their equipment, telegraph paper caught fire from induced electrical currents, and auroras were seen as far south as the Caribbean. The world was largely pre-electric then, so the damage was limited to a fascinating and frightening spectacle. A similar storm today would be a global catastrophe of a different magnitude. Our civilization now runs on a vast, interconnected web of vulnerable technology. A massive CME striking Earth's magnetosphere would induce powerful electrical currents in our long-distance power lines, potentially overloading and destroying transformers, the massive, hard-to-replace components that form the backbone of the electrical grid. A widespread, prolonged blackout could last for months or even years as we struggle to rebuild this critical infrastructure. Simultaneously, the intense radiation from such an event would fry the delicate electronics in thousands of satellites, wiping out GPS, global communications, weather forecasting, and financial networks in an instant. We would be plunged into a technological dark age with cascading failures in food distribution, water treatment, and emergency services. This is not science fiction. It is a documented risk that drives a multi-billion-dollar effort to understand and predict our star's behavior. We now have a fleet of solar sentinels watching the Sun 24/7. The Solar and Heliospheric Observatory, or SOHO, has been a vigilant guardian for decades, providing early warnings of solar eruptions. And now we have a daring explorer flying into the fire. NASA Parker Solar Probe is performing an unprecedented mission, diving repeatedly through the Sun's outer atmosphere, the corona, to directly sample the solar wind and magnetic fields where these storms are born. Its data is helping us understand the fundamental physics that drives solar weather, moving us from simple observation toward true forecasting. The discovery of solar weather's potential impact is a sobering lesson in cosmic humility. It reminds us that our technological prowess has, in many ways, made us more fragile, not less. Our greatest inventions are susceptible to a force that has existed for billions of years. This knowledge is not meant to frighten, but to motivate. By learning to predict these solar outbursts, we can develop the safeguards, the hardened infrastructure, and the contingency plans to weather the storm. We are learning to read the Sun's mood, not as passive observers, but as a civilization determined to secure its future against the beautiful, violent heart of our solar system. The violent beauty of our Sun reminds us that survival is not guaranteed, even for a species that has mastered its home world. This leads us to one of the most profound and unsettling questions in all of science, a question posed by physicist Enrico Fermi over a simple lunch conversation. If the universe is so unimaginably vast and old, with billions of planets that could harbor life, then where is everybody? This is the Fermi paradox. The math is overwhelmingly on the side of life. With hundreds of billions of stars in our galaxy alone, many with planets, and the universe itself over 13 billion years old, it seems statistically inevitable that intelligent civilizations should have arisen many times over, and many of them millions or even billions of years ahead of us. They would have had ample time to spread across the galaxy, to build artifacts we could see, or to send signals we could hear. Yet when we look up and listen, we are met with a profound and echoing silence. The cosmos appears empty, quiet, and strangely still. This contradiction between high probability and zero evidence is the heart of the paradox, and its solutions are not just scientific, they are deeply philosophical, forcing us to confront our own place and potential fate. One of the most sobering explanations is the concept of the Great Filter. This is the idea that there is some critical, nearly insurmountable step in the evolution of life from simple chemistry to a spacefaring civilization. The filter could lie in our past. Perhaps the jump from non-living chemistry to the first self-replicating cell is astronomically rare, a miracle of chance that happened here but almost nowhere else. Or perhaps the filter is where we are right now. The transition from a tool using species to a stable, technological civilization that does not destroy itself with its own power, whether through nuclear war, engineered pandemics, or environmental collapse, could be the step that almost no one passes. In this view, the eerie silence is a cemetery of civilizations that failed to make the leap. The filter could also lie ahead of us, a future challenge so difficult that it has stopped every civilization that came before. Another set of answers suggests the problem is not with their existence, but with our ability to perceive them. A civilization a million years more advanced than ours might use technologies and communicate in ways we cannot begin to recognize. Their signals might not be simple radio waves, but something far more sophisticated, like modulated neutrinos or gravitational waves, channels we are only now learning to tune into. Or perhaps they have moved beyond physical expansion, uploading their consciousness into vast, efficient virtual realities, leaving the outside universe quiet and dark. They might practice a form of cosmic conservation, choosing not to broadcast their presence to a potentially dangerous galaxy. Or, in a more haunting thought, we might be living in a kind of cosmic zoo or wildlife preserve, deliberately isolated by a galactic community that has decided to observe us until we reach a certain maturity. The Fermi paradox forces a mirror upon humanity. It asks us to consider whether our current technological adolescence is a fleeting, dangerous phase that most species do not survive, or if it is the first step on a much longer journey. That silence we hear is not empty, it is filled with questions about our own destiny. Are we alone because life is a fragile spark in a dark wind, or are we simply too young to understand the conversation happening all around us? The answer, whichever it may be, will redefine what it means to be human in a cosmos that is either waiting for us or waiting for us to disappear. That profound cosmic silence might not mean life is rare, only that its journey is far more ancient and interconnected than we ever dreamed. The theory of panspermia proposes a radical idea: life, or at least its essential building blocks, does not have to originate on the planet where it thrives. Instead, it can be a cosmic traveler, hitching rides on meteoroids, asteroids, or comets, seeding life from one world to another. This transforms life from a local phenomenon into a potential galactic epidemic, spreading its genetic code across the vast distances between stars. The evidence for this begins right here on Earth with rocks that fell from the sky. For decades, scientists have been analyzing a special class of meteorites called carbonaceous chondrites. These are not just lumps of metal and stone, they are time capsules from the early solar system, packed with organic material. Inside them, researchers have found a rich array of amino acids, the very molecules that link together to form proteins, the workhorses of all known biology. These are not the products of earthly contamination. They have distinct chemical signatures proving they formed in space. The Murchison meteorite, which fell in Australia in 1969, contained over 90 different amino acids, including many that are common in terrestrial life. This discovery is monumental. It tells us that the basic chemical ingredients for life are being manufactured in abundance in the cold, dark molecular clouds of space and delivered, ready-made, to the surfaces of young planets. The universe, it seems, is pre-stocked with the Lego bricks of biology, but could the bricks assemble themselves into something more during the journey? Experiments on the International Space Station have tested the hardiness of life itself in the void. Researchers exposed colonies of extremophile bacteria, like the incredibly resilient Deinococcus radiodurans, to the raw conditions of space for years. These microbes were subjected to the complete vacuum, extreme temperature swings, and the unshielded cosmic and ultraviolet radiation that would instantly kill almost any other organism. Astonishingly, when retrieved, many of these bacterial colonies had survived, protected in tiny cracks within the rock or under just a thin layer of material. If a clump of these hardy bacteria were nestled deep inside a rock blasted off a planet by an asteroid impact, they could potentially survive an interstellar voyage lasting millions of years, entering a dormant state until they crash-landed on a new, welcoming world. This leads to a breathtaking and humbling possibility. We know that in the solar system's violent youth, massive impacts routinely ejected material from the surfaces of planets. Rocks from Mars have been found on Earth, identified by the unique chemical signature of the Martian atmosphere trapped inside them. Given what we now know about early Mars being a wet, potentially habitable world, could it have been the true cradle of life? If microbial life arose there first, a large impact could have hurled a life-bearing Martian rock into space, where it drifted until it eventually landed on a young, watery Earth, inoculating our planet with a Martian biosphere. In this scenario, we would all be descendants of Martians. The reverse is also true. Earth rocks have undoubtedly reached Mars, Venus, and the moons of the outer planets over the eons. If life ever existed on Earth before a cataclysm, or if hardy microbes were carried away on ejector, we may have already seeded life elsewhere in our own solar system without ever knowing it. Panspermia reshapes the entire narrative of life's history. It suggests that the spark of life may need to ignite only once in a favorable stellar nursery. From that single genesis, asteroid impacts become nature's spacecraft, and comets its delivery vehicles, spreading biological potential across entire star clusters. A single living world could, over billions of years, become the parent to an entire family of life-bearing planets. This means life on Earth may not be a solitary miracle, but a branch on a vast, ancient, and interstellar family tree. The search for life on Mars or Europa then becomes a search for our own cosmic cousins. That ancient interstellar family tree has roots stretching back to the very first moment of everything. To understand our cosmic lineage, we must listen for the faintest possible whisper, the fading echo of creation itself. This is the cosmic microwave background, the oldest light in the universe. It is the afterglow of the Big Bang, a relic from a time when the entire cosmos was a searing, opaque plasma, just 380,000 years old. As the universe expanded and cooled, protons and electrons combined to form the first neutral atoms, and suddenly, light could travel freely. That first flash, once brilliant and hot, has been stretched by the relentless expansion of space over 13.8 billion years, cooling into a faint, uniform microwave glow that permeates every corner of the sky. It is the cosmic fossil radiation, and it holds the blueprint for everything that followed. For decades after its accidental discovery, the CMB appeared as a smooth, featureless sea of microwaves. But our satellites have given us new eyes. The Wilkinson Microwave Anisotropy Probe, or WMAP, and later the European Space Agency's Planck mission, mapped this ancient light with breathtaking precision. They revealed that the background is not perfectly smooth. It is etched with tiny, mottled variations in temperature, fluctuations of just a few millionths of a degree. These are not random imperfections, they are cosmic hieroglyphs. These minute-hot and cold spots are the imprint of quantum fluctuations from the universe's first trillionth of a second, seeds magnified by a period of hyper-expansion called inflation. They are the gravitational seeds from which all cosmic structure grew, the slight over-densities that would, over eons, pull in matter to form the first galaxies, stars, and eventually us. By decoding the precise patterns in this light, cosmologists have read the universe's birth certificate. The distribution and size of the fluctuations tell a complete story of the cosmos's geometry, composition, and history. The data reveals a universe that is geometrically flat on the largest scales, meaning parallel lines never meet, and the rules of Euclidean geometry we learned in school hold true across the cosmos. This flatness is a critical clue, telling us the total density of matter and energy in the universe is exactly balanced on a razor's edge. The composition it reveals is the most humbling part. Ordinary matter, the atoms that make up stars, planets, and us, accounts for a mere 5% of the universe. 27% is the mysterious dark matter that binds galaxies, and a whopping 68% is dark energy, the enigmatic force accelerating the expansion of space itself. This precise recipe, written in the faint microwaves, also gives us the universe's age with remarkable certainty, 13.8 billion years. The cosmic microwave background is the ultimate foundation of modern cosmology. It is the single most important piece of evidence we have for the Big Bang model, a snapshot of the infant universe that confirms our deepest theories about its origin and evolution. Every galaxy, every star, every planet, and every living thing is a later elaboration on a theme first written into that primordial light. When we look at the detailed map from Planck, we are not just looking at a scientific dataset, we are staring directly at the afterimage of creation, seeing the universe as a newborn, and reading the destiny that would unfold over billions of years. It is our most direct connection to the beginning of everything. The afterglow of creation gave us a universe, but what shaped its grandest cities, the galaxies themselves? At the very heart of nearly every large galaxy, including our own Milky Way, lies a gravitational monster of almost incomprehensible scale. This is the supermassive black hole, an object millions or even billions of times more massive than our Sun, compressed into a region of space smaller than our solar system. For decades, these giants were theoretical phantoms, their presence inferred only by the frantic dance of stars whipping around an invisible, titanic mass at the galactic center. Then, in April 2019, a global collaboration called the Event Horizon Telescope did the impossible. It presented humanity with our first direct image of a black hole's shadow, the dark silhouette of the supermassive beast at the core of the galaxy M87, framed by a swirling, fiery ring of superheated gas. That single, blurry orange donut was a landmark of human ingenuity, a visual confirmation of the darkest prediction of Einstein's gravity. But these black holes are far more than just cosmic vacuum cleaners. They are the hidden engines of galactic evolution, and their activity may write the very life story of the stars around them. When a supermassive black hole actively feeds, pulling in vast amounts of gas and dust, the infalling material doesn't just vanish. It forms a swirling, luminous accretion disk and often powerful jets of radiation and particles that can blast out across thousands of light years. This outpouring of energy is so colossal it can heat the surrounding galactic gas, preventing it from cooling and collapsing to form new stars. In this way, a voracious black hole can effectively shut down star birth in its host galaxy, turning a vibrant, star-forming spiral into a quiet, red and dead elliptical. Conversely, the shock waves from these jets might also trigger star formation in dense clouds farther out, compressing the gas just enough to ignite new stellar nurseries. The supermassive black hole, it seems, acts as a cosmic regulator, a gravitational heart whose beats of activity help determine whether a galaxy thrives with young, blue stars or fades into a retirement home of ancient red ones. Our own galactic center, Sagittarius, a star, is relatively quiet today, but evidence suggests it had violent feeding frenzies in the past, its outburst shaping the environment we now inhabit. Studying these objects pushes physics to its absolute limit. The region just outside a black hole's event horizon is where gravity ceases to behave by our familiar rules, where space and time are twisted into knots. Observations of stars orbiting our own galactic center and images like that of M87 allow us to test general relativity in its most extreme regime. They ask fundamental questions: what happens to information that falls in? What is the true nature of the singularity at the center? The supermassive black hole is not a passive occupant of the galactic core. It is the architect, the silent governor, whose immense gravity and occasional fury have sculpted the majestic island universes we see across the cosmos. Our galaxy is not drifting in solitude. The Milky Way, along with our entire local group of galaxies, is caught in a vast, silent river of motion, all flowing toward a single, mysterious point in the darkness. This is the Great Attractor, a gravitational anomaly of such immense power it is pulling hundreds of thousands of galaxies, including our own, toward a region of space we cannot even see. The discovery came from mapping the subtle, yet consistent, deviations in the universal expansion. While most galaxies are receding from us in the general flow of the cosmic expansion, detailed surveys revealed a peculiar bulk flow, a shared drift of countless galaxies in one particular direction, toward the constellations of Centaurus and Hydra. It was as if we had found a colossal waterfall in the ocean of space, a current dragging everything toward a hidden drain. But when astronomers pointed their telescopes toward the source of this pull, they were met with a frustrating blank spot. The Great Attractor lies directly behind the plane of our own Milky Way, in a region called the Zone of Avoidance. Here, the thick dust and dense starfields of our galaxy's spiral disk block our optical view, creating a blind spot that obscures nearly 20% of the extragalactic sky. For years, the heart of this immense pull remained a shadow, a ghost inferred only by its gravitational influence on everything around it. To peer through this cosmic curtain, scientists had to switch to eyes that see through dust using radio, infrared, and X-ray telescopes. What they found was not a single monstrous object, but something even more profound. The Great Attractor appears to be the core of the Laniakea supercluster, our home supercluster of galaxies. It is a gravitational focal point, a vast overdensity where the pull of many massive galaxy clusters, like the Norma cluster, combines with an unimaginably large concentration of dark matter. This dark matter forms the hidden skeleton of the cosmic web, and at this nexus, its gravitational well is so deep it dictates the motion of galaxies for hundreds of millions of light years in every direction. We are not being pulled toward a devouring void, but toward the center of mass of our own immense neighborhood in the universe. This discovery is a humbling lesson in cosmic perspective. Even as we chart the expansion of the entire universe, we are simultaneously caught in a local current, a gentle but undeniable tug that reminds us we are part of a hierarchy of structures far grander than we can easily see. The Great Attractor reveals that the universe has texture and flow on the largest scales, with gentle gravitational hills and valleys sculpted by dark matter, guiding the grand migration of galaxies through the void. It is a silent testament to the fact that the forces shaping our cosmic journey are often hidden, operating behind veils of light and dust, reminding us that the map of the cosmos is still being filled in, one mysterious pull at a time. The silent river of galaxies pulls us toward an unseen center, but far from any star's light, an even lonelier population drifts through the endless night. These are rogue planets, entire worlds that have been torn from their stellar orbits or formed in isolation, now wandering the interstellar darkness untethered to any sun. They are cosmic nomads, invisible to traditional telescopes, their existence revealed only by a subtle trick of gravity. When one of these dark planets passes in front of a distant star, its gravity acts as a fleeting lens, bending and magnifying the star's light for a few days or hours in an event called microlensing. Surveys like those from the optical gravitational lensing experiment have caught these telltale flashes, and the statistical results are staggering. The data suggests there could be billions, perhaps even trillions, of these free-floating worlds adrift in our galaxy alone, possibly outnumbering the stars themselves. This reveals a hidden demographic of the cosmos, a vast sea of orphaned worlds we never knew existed. What are these lonely travelers like? Cut off from the warmth of a star, their surfaces would be plunged into a deep, perpetual freeze where temperatures hover just a few degrees above absolute zero. Any atmosphere would likely have collapsed into a frozen crust, leaving a barren, airless landscape under a sky of unbroken black, illuminated only by the faint, diffuse glow of the Milky Way. They seem like the ultimate dead worlds, yet for some there might be a hidden spark of warmth. Larger rogue planets, especially those with rocky iron compositions, could retain heat from their violent formation and from the ongoing decay of radioactive elements in their cores. This internal warmth could be enough to maintain a global ocean of liquid water beneath a thick, insulating shell of ice, creating a sealed, sunless abyss not unlike the subsurface sea of Europa, but utterly isolated in the void. The possibility is haunting that life could exist in these pitch-black internal oceans, ecosystems fueled entirely by geothermal heat and chemistry, completely unaware of the concept of a sun or a sky. As we look toward an interstellar future, these rogue planets represent both a profound mystery and a practical consideration. They are a vast, unexplored population of celestial bodies, each a potential laboratory for exotic geology and chemistry. They could also serve as way stations or resource depots for generations-long voyages between stars, offering raw materials and perhaps even water ice for fuel. Yet their darkness also makes them a navigational hazard, invisible icebergs in the sea of space that a future starship would need to chart and avoid. Their sheer number forces us to expand our definition of a planet and reconsider the cosmic census. We have long defined planets by their relationship to a star, but these wanderers challenge that notion, belonging only to the galaxy itself. Each one is a silent testament to the chaotic dynamics of young solar systems, where gravitational encounters can fling worlds into the eternal night. Their discovery asks us a quiet, profound question. In the absolute darkness between the stars, what other lonely wonders are waiting unseen? While rogue planets drift in darkness, a different mission is illuminating the entire galactic neighborhood with stunning clarity. The European Space Agency's Gaia spacecraft is performing a census of cosmic proportions, one that is fundamentally rewriting our map of the Milky Way. Since its launch, Gaia has not simply been taking pictures of stars, it has been measuring them with a precision once thought impossible. Its mission is to repeatedly scan the sky, pinpointing the positions, distances, and motions of over 1 billion stars, more than 1% of our galaxy's entire stellar population. The result is not a static snapshot, but a living, breathing, three-dimensional movie of our galactic home in motion. Before Gaia, our view of the Milky Way was akin to trying to map a vast forest while standing in the middle of it, with most trees obscured by fog. We had rough estimates and models, but precise distances to stars were notoriously difficult to measure, leaving our understanding of the galaxy's true architecture vague and incomplete. Gaia has lifted that fog. By measuring a star's parallax, the tiny apparent shift in its position as Earth orbits the Sun, Gaia calculates its distance with extraordinary accuracy. Simultaneously, its instruments gauge the star's motion across our line of sight, its proper motion, and its velocity toward or away from us through spectroscopy. This trifecta of data transforms anonymous points of light into individual celestial citizens with known addresses and trajectories. The revelations have been breathtaking. Gaia's data has allowed astronomers to construct the most detailed map ever of the Milky Way's spiral arms, confirming their structure and revealing new substructures and stellar streams. These streams are like rivers of stars, the ghostly remnants of smaller galaxies that were torn apart and absorbed by the Milky Way's gravity billions of years ago. By tracing the motions of these stars backward in time, we can now literally watch the galactic mergers of the past unfold, reconstructing the violent history of our galaxy's growth. This is archaeology on a galactic scale. Furthermore, Gaia is exposing the dynamic aftermath of the Milky Way's last major collision. The data clearly shows that a significant portion of stars in our galactic halo are not moving randomly, but are part of a vast, disrupted dwarf galaxy now known as the Gaia Sausage or Enceladus, which merged with the Milky Way roughly 10 billion years ago. This event likely stirred up the galaxy's gas, triggered intense bursts of star formation, and may have even contributed to the structure of our galactic disk. Gaia is revealing that our galaxy is not a serene, isolated island, but a product of a violent and ongoing construction project, with the scars and souvenirs of ancient collisions still visible in the paths of its stars. The mission's impact extends far beyond galactic cartography. By providing precise distances to countless stars, Gaia acts as a foundation for all of astronomy. It calibrates the cosmic distance ladder, improves our understanding of stellar evolution by showing us stars of exact ages and compositions, and even aids in the hunt for exoplanets by characterizing their host stars with perfect clarity. The Gaia revolution is one of perspective. It is transforming our home galaxy from a vague, two-dimensional illustration into a precise, three-dimensional engine whose history is written in the moving paths of 1 billion suns. We are no longer just inhabitants of the Milky Way, we are now its biographers, watching its story unfold in real time. The search for life is not limited to biology alone. As we scan the cosmos, we are also beginning to look for the fingerprints of intelligence, the industrial signatures of a civilization that has mastered its world and perhaps its star. These are called technosignatures, and they represent a bold new frontier in our quest to find company in the universe. While biosignatures like oxygen and methane hint at microbes or plants, technosignatures would point to engineers, builders, and astronomers. The most familiar idea is the search for deliberate radio or laser signals, a direct hello. But technosignature science casts a much wider net, looking for the unintended side effects of a civilization's daily life, the cosmic pollution or megastructures that might be visible across interstellar distances. Imagine, for example, the glow of a planet's night side. Earth, as seen from afar, is not dark on the night side. Our cities blaze with artificial light, a clear signature of widespread energy use and organization. A future telescope with extraordinary sensitivity might one day detect an unnatural, patchy glow on the night side of an exoplanet, the collective illumination of alien metropolises. Another potential marker lies in the air itself. Our industrial age has filled Earth's atmosphere with chemicals that do not belong there naturally, like chlorofluorocarbons from refrigerants or nitrogen dioxide from combustion. These are powerful greenhouse gases with distinct spectral fingerprints. If we were to detect such industrial pollutants in the atmosphere of a world otherwise in a natural state, it would be a startling sign of an active technological society, one perhaps unaware it is broadcasting its presence to the galaxy. Then there are the concepts that stretch our imagination to its limits, the megastructures envisioned by physicists like Freeman Dyson. A Dyson sphere or swarm is not a solid shell, but a vast constellation of energy collecting satellites orbiting a star, capturing a significant fraction of its light to power a civilization's immense needs. From our vantage point, such a structure would cause a star to behave bizarrely. It would grow dim, not in the regular, repeating rhythm of a planet transit, but in an irregular, deep, and perhaps permanent way, while glowing faintly in the infrared from the waste heat of all that captured energy. Astronomers have already found stars with inexplicable dimming patterns, like the famous Boyajian star, whose wild fluctuations sparked theories of alien megastructures, though natural explanations like swarms of comets are more likely. The search for these signatures is not a replacement for traditional SETI, but a vital expansion. It acknowledges that an advanced civilization might not be actively signaling us, or might use communication methods we cannot yet comprehend. Instead, they might simply be going about their business, and the sheer scale of that business could make them visible. This forces us to think on a truly galactic timescale. A civilization that survives for millions of years would inevitably reshape its environment, perhaps its entire star system, in ways that become detectable. Their markers might be the subtle traces of resource extraction, the glint of vast orbital habitats, or even the redirected light of stars being used for propulsion. Looking for technosignatures reframes the question from "are they calling us?" to "what have they built?" It turns the cosmos into a silent construction site, and we are the inspectors, looking for the telltale signs of work in progress, or the enduring monuments of a project completed eons ago. The search for technosignatures asks what other builders have created, but a deeper mystery asks why our own cosmic workshop seems so perfectly arranged for our existence. This is the puzzle of fine-tuning, the fundamental constants of our universe, the numbers that govern gravity, the strength of nuclear forces, and the mass of elementary particles, appear to be exquisitely balanced on a razor's edge. If the force that binds atomic nuclei were even slightly stronger, all the hydrogen in the early universe would have fused into heavier elements, leaving no fuel for stars. If it were slightly weaker, complex atoms could never form at all. If gravity's strength were tweaked by a minuscule fraction, stars would either burn out in a flash or never ignite. This precise calibration seems too perfect to be mere accident, leading to a profound and unsettling question. Why does the universe have a set of rules that allows for galaxies, stars, planets, and ultimately, observers like us? One compelling, yet deeply speculative, answer to this riddle is the multiverse hypothesis. This idea emerges from the edges of our most successful theories. The prevailing model of cosmic inflation suggests that our entire observable universe is just one bubble in a frothing, eternal sea of spacetime. In this endless cosmic foam, new bubble universes are constantly budding off, each with its own random set of physical laws and constants. Most of these universes would be stillborn or barren, expanding into empty voids or collapsing instantly. But in a near-infinite ensemble of universes, by sheer statistical chance, a tiny fraction would, like ours, stumble upon the rare combination of numbers that permits complexity and life. We find ourselves in one of those lucky universes not because it was designed, but because we could not exist anywhere else. This is the anthropic principle in a cosmic context. String theory, a leading candidate for a theory of everything, adds further weight to the idea. It suggests there may be a staggering number of possible stable configurations for the extra dimensions it proposes, perhaps 10 to the 500 different solutions, each corresponding to a universe with different physics. Our universe, then, would be just one possibility in a vast landscape of potential realities. While the multiverse remains a theoretical framework without direct experimental proof, it represents a legitimate scientific attempt to grapple with the eerie fine-tuning we observe. It pushes cosmology into a realm that blends physics with philosophy. If true, it would represent the ultimate Copernican revolution, demoting our entire universe from the singular stage of reality to a single page in an infinite library of cosmic histories. The implications are staggering. Every possible version of events that physical laws allow could be playing out somewhere in the multiverse. There could be universes where gravity repels, where time flows backward, or where the very concept of matter is unrecognizable. While we may never have direct evidence of these other realms, the multiverse hypothesis forces a humbling perspective. It suggests that the laws we consider immutable and fundamental may be nothing more than local bylaws, the parochial customs of our own cosmic neighborhood. This idea, born from the equations of inflation and string theory, challenges our deepest notions of reality. It turns the question of why our universe is the way it is from a search for a single answer into a statistical inevitability in an unimaginably vast ensemble. The multiverse may forever lie beyond our observational horizon, but as a concept, it expands the canvas of existence to its absolute limit, asking us to consider that everything we know is just one possibility in a silent, infinite sea of alternate realities. The search for cosmic answers often requires us to build new tools, and some of the most revolutionary are now operating not just to observe the universe, but to rewrite the rules of our own global conversation. Orbiting silently above the Earth, a new class of satellite is conducting experiments that sound like science fiction, using the bizarre laws of quantum mechanics to create a new kind of internet, one whose security is guaranteed by the fundamental nature of reality itself. This is the promise of quantum communication, and it took a leap into space to prove it was possible. The challenge was distance. On Earth, sending quantum particles like individual photons of light through fiber optic cables is a fragile process. Over just a few dozen miles, the photons are absorbed or scattered, their delicate quantum states destroyed. To create a truly global quantum network, scientists realized they needed to go above the atmosphere. In 2016, China launched the Misha satellite, a pioneering mission named after an ancient philosopher. Its goal was to perform quantum experiments across unprecedented distances. The core technology it tested is called quantum key distribution. Here is how it works in principle. Instead of sending an encrypted message itself, you send the key to decrypt it, but you encode that key into the quantum properties of individual photons. This could be in the polarization or the angle of their light waves. According to quantum mechanics, the mere act of observing such a particle inevitably alters its state. So if a hacker tries to intercept the key, they will unavoidably change the photons, introducing errors that the legitimate sender and receiver can immediately detect. They would know the line was tapped and simply discard that key, making the interception both obvious and useless. The security is not based on complex mathematics that could someday be cracked by a powerful computer, but on the unbreakable laws of physics. Missions turned this theory into a stunning reality. The satellite generated pairs of entangled photons, particles whose properties are mysteriously linked across any distance. It then beamed one photon from each pair to a ground station in China and the other to a station in Austria, separating them by over 4,600 miles. Using these entangled particles, the teams in both countries were able to generate identical, secret cryptographic keys, a process secured by the quantum link between the satellite and Earth. They then used those keys to conduct the world's first intercontinental quantum-secured video call. This was not just a record, it was a paradigm shift, proving that space is the essential medium for a future quantum internet. The vision this enables is profound. Imagine a future network where satellites act as trusted nodes in the sky, linking quantum computers and secure communication hubs on every continent. Sensitive data, from national security secrets and financial transactions to personal medical records, could be transmitted with a level of security we can barely comprehend today. This quantum backbone would be immune to the threats posed by future machines like quantum computers, which could potentially break the classical encryption that currently guards our digital world. The vacuum of space is the ideal environment for this, as photons can travel vast distances without the interference they face in cables or the turbulent atmosphere near the ground. We are witnessing the birth of an entirely new infrastructure for human connection, built not on silicon and code alone, but on the spooky, non-local handshake of entangled particles. This is more than a technical achievement, it is a philosophical one. We are harnessing the most counterintuitive rules of the microscopic realm, rules that govern the behavior of the universe at its smallest scales, and using them to construct a global system of trust. The satellites now being designed and launched are the first nodes in a web that will one day envelop the planet, a silent network where every bit of information is guarded by the immutable laws of quantum physics. The ultimate test of our cosmic ambitions will not be in reaching another world, but in learning how to stay there. This is the promise of in situ resource utilization, a technical term for a profoundly simple idea: living off the land. Instead of hauling every drop of water, every breath of air, and every brick for a shelter on a multi-billion-dollar rocket from Earth, we are learning to manufacture these essentials from the raw materials waiting for us on other worlds. This discovery transforms distant planets from hostile destinations into potential homesteads, and the technologies to make it happen are already being proven. On the red, dusty surface of Mars, a toaster-sized instrument aboard the Perseverance rover is conducting a quiet revolution. It is called MOXIE, the Mars Oxygen In Situ Resource Utilization Experiment. Its task is elegantly straightforward, yet revolutionary: to suck in the thin Martian air, which is 95% carbon dioxide, and electrochemically split those molecules, producing pure, breathable oxygen. In multiple tests, MOXIE has done exactly that, generating oxygen at a purity level that would be suitable for both life support and, critically, rocket fuel. Oxygen is the heaviest component of rocket propellant, making up about 80% of the mass needed to launch a crew from the Martian surface back to orbit. Producing it locally means future astronauts could manufacture their own return ticket, slashing the mass and cost of the initial mission by an enormous factor. MOXIE is a small-scale prototype, but its success is a giant leap in practicality, proving that we can literally make air from an alien sky. Meanwhile, on the Moon, the focus is on the soil itself. Lunar regolith, that fine, abrasive dust that covers the surface, is not just a nuisance for astronauts, it is a resource. Experiments on Earth using simulated lunar soil have demonstrated a process called molten regolith electrolysis. Imagine taking a scoop of this gray powder, placing it in a chamber with an electrode, and heating it to extreme temperatures until it melts. Once molten, an electric current passed through it can trigger a chemical reaction, breaking the soil apart and releasing oxygen gas that bubbles to the surface, while leaving behind useful metals like iron and silicon. This process could provide not only oxygen for breathing and fuel, but also raw materials for construction. And that leads to the next critical piece of the puzzle: building shelters. The idea of launching prefabricated habitats from Earth is massively inefficient. Instead, agencies are pioneering the use of 3D printing technology, using regolith itself as the ink. Large robotic printers could use microwaves or lasers to sinter or fuse layers of lunar or Martian soil into solid, durable structures. These printed habitats could take the form of domes or underground chambers, using the local material as a shield against cosmic radiation and micrometeorites. Tests on Earth have already produced small-scale demo structures using soil simulants, proving the concept is viable. The vision is a self-sufficient outpost where robots, deployed ahead of human crews, use solar power to extract oxygen from the soil and print the first basic habitats, preparing the site for arrival. This shift in thinking is fundamental. For all of spaceflight history, every mission has been a camping trip where you bring absolutely everything you need with you. In situ resource utilization is the discovery that changes the paradigm from camping to settling. It is the difference between being a visitor who packs all their food and a settler who plants a garden. The implications for sustainability are staggering. A permanent lunar base or a Martian colony becomes economically and logistically plausible when it can produce its own air, water, and building materials, needing only periodic shipments of complex machinery or specialized goods from Earth. This technology also has a profound echo for our own planet, driving advances in closed-loop life support systems, efficient resource recycling, and low-energy manufacturing that could benefit communities in extreme environments on Earth. The discovery that we can use what we find in space is the key that unlocks the solar system. It tells us that the universe provides the tools, we just need to learn the local instructions. The dream of a sustained human presence beyond Earth is no longer a question of if we can carry enough, but of how cleverly we can use what is already there. From the practicalities of survival on other worlds, we are drawn back to the most fragile and precious world of all. In 1990, from a distance of 3.7 billion miles, the Voyager 1 spacecraft turned its camera homeward for one final look. What it captured was not a detailed map or a brilliant blue marble, but a single, pale blue pixel, a mote of dust suspended in a sunbeam. That image, and Carl Sagan's reflection upon it, became a seismic event for the human spirit. He saw our planet not as a stage for division, but as a lonely speck, the only home we have ever known. Every human being who ever lived, every triumph and tragedy, every empire and forest, all existed on that barely visible dot. This perspective, forged in the cold void of space, is perhaps the most transformative discovery of all, for it carries no data about distant stars, but an urgent truth about ourselves. It collapses all borders, not through politics, but through sheer, undeniable scale. Seen from the edge of our solar system, national boundaries vanish, and the thin, glowing atmosphere becomes a shared and fragile bubble protecting all of life. This is not an abstract idea, it is a visceral reality check. That pale blue dot holds everything we love and everything we are. All our conflicts, our sprawling cities, our diverse ecosystems are contained within that single, vulnerable point of light. This cosmic viewpoint fosters a profound sense of planetary citizenship. It argues that environmental stewardship is not a national duty, but a species-wide imperative. The climate systems, the oceans, and the biosphere do not recognize flags. They are the interconnected life support system for the pale blue dot. When we see Earth from this distance, the necessity of international cooperation shifts from an ideal to a simple matter of practical survival. Space exploration, ironically, gives us the ultimate reason to care for our own planet. It shows us both our cosmic insignificance and our irreplaceable value. We are insignificant in the vast theater of the universe, a tiny audience on a speck of dust. Yet we are also the universe become conscious, looking back at itself. That duality is powerful. It humbles our ego while elevating our responsibility. The image reminds us that in all our searching across the solar system, we have found no other garden, no backup plan, no second chance. This discovery, this emotional and philosophical shift in awareness, is the quiet engine behind so much else. It is the reason we build climate models, protect biodiversity, and strive for peaceful collaboration in science. It is the understanding that every environmental treaty, every conservation effort, is an act of loyalty to that tiny, pale blue speck. The Voyager probe is now in interstellar space, carrying a golden record with sounds and images of Earth, a message in a bottle tossed into the cosmic ocean. But its greatest gift was not what it sent out, but the picture it sent back, a mirror held up to humanity from the depths of space. That reflection tells us we are alone together, adrift in the immense and beautiful dark, with only each other and this fragile, glowing world to call home. Our shared home, that pale blue dot, is now telling a new story about itself, and the narrator is us. The final discovery in this cosmic journey is not found in a distant galaxy or on a frozen moon, but in the unmistakable signature of our own civilization, visible from orbit. We have entered a new geological epoch, the Anthropocene, where humanity is the dominant force shaping the planet's surface and atmosphere, and space-based observation is the ultimate witness. Satellites circling the Earth provide a continuous, global audit of our impact, delivering data with a clarity that is both humbling and essential. They show the Amazon rainforest not as an unbroken green carpet, but as a patchwork quilt with geometric scars of deforestation cutting deep into the jungle, fragments of a disappearing world. At night, the planet does not sleep, it ignites. Vast networks of electric light trace the outlines of continents, with brilliant webs marking cities and highways, a stark map of human energy consumption that bleeds into the darkness where wild lands used to be. The polar ice caps, those ancient reflective shields, are in retreat. Time-lapse imagery from space shows the Arctic sea ice shrinking summer after summer, a dramatic reduction in both extent and thickness, while the great ice sheets of Greenland and Antarctica hemorrhage trillions of tons of meltwater into the rising oceans. Perhaps most critically, satellites like Japan's GOSAT and NASA OCO2 do not just take pictures, they take the planet's breath. They map the global concentration of carbon dioxide and methane in the atmosphere, revealing the invisible blanket of greenhouse gases thickening year by year. These are not models or predictions, they are direct measurements, an irrefutable chemical fingerprint of our industrial age. This space-based perspective collapses time and distance, giving us a god's-eye view of planetary change. We can watch a glacier calve an iceberg the size of a city in real time, track the intensification of hurricanes over warming seas, and monitor the creeping advance of deserts. This constant vigil provides the undeniable evidence that climate change is not a localized or debatable phenomenon. It is a whole Earth event unfolding now. Yet this sobering surveillance also holds our greatest hope. This same global monitoring network is the tool we need to manage the crisis. It allows scientists to pinpoint major sources of emissions, track the health of global forests that act as carbon sinks, and verify international agreements on pollution reduction. It enables precision agriculture to use less water, helps coastal cities plan for sea level rise, and monitors air quality to protect public health. The view from space strips away denial and lays the truth bare, but it also empowers action with unprecedented knowledge. The Anthropocene from space presents us with a profound duality. We are the first species to see our own planetary footprint in its terrifying totality, and we are the first species with the technological capacity to understand and alter that trajectory. The pale blue dot is no longer just a fragile oasis adrift in the dark. It is a world being actively rewritten by the hands of its most conscious inhabitants. The data streaming down from orbit is a mirror, a report card, and a blueprint all at once. It asks us a final, urgent question. Now that we can see the full scope of our power, will we choose to be remembered as the force that destabilized our only home, or as the generation that looked clearly at the evidence and mustered the wisdom to heal it? The next chapter of Earth's story is not written in the stars, but in the choices we make here, guided by the unblinking eyes we have placed in the sky. From the chemistry of distant atmospheres to the silent pull of dark matter, these 30 discoveries paint a portrait of a cosmos in constant, astonishing conversation with our own small world. We have charted hidden oceans within frozen moons, listened for the echoes of colliding black holes, and traced our own elemental origins to the fiery hearts of dying stars. We have confronted the possibility that we are not alone, and the equal possibility that we are tragically unique. This journey reveals a fundamental truth: space science is not a distant abstraction. It is the story of us. It is the search for our cosmic ancestry written in the light of the first dawn, and the practical blueprint for our survival written in the water ice of the Moon and the thin air of Mars. Every new map of the galactic web, every analysis of an exoplanet's atmosphere, every gram of oxygen produced from Martian soil changes life on Earth. It changes our technology, giving us quantum-secured networks and warnings of solar storms. It changes our economy, pointing toward the asteroid mines and orbital depots of tomorrow. Most profoundly, it changes our perspective, shrinking our conflicts under the gaze of the pale blue dot, while expanding our sense of home to encompass an entire living solar system. The universe is not a static backdrop. It is an active participant in our destiny, offering both dire warnings and boundless gifts, so keep looking up. Support the science that turns wonder into understanding. Nurture the curiosity that asks the next great question, because the next revelation, the one that will once again redefine our place in the grand scheme, is already drifting in the void or hidden in the data, waiting for a human mind to find it. The greatest discoveries are not behind us, they are ahead, lighting the way forward.